Okay, folks. So here we are. We have an introduction to the logic under probit regression. We know that we've done most of the theory so far, and what we are going to do is really see a practical example with, of course, soft code from R. Okay. So the outcome is, of course, there's an outline here. We'll have an introduction and description of the problem, some potential problems and solutions, and how do you write up the results of a logistic regression model. Why use logic and probit regression? That's what we're going to talk about. How do you experiment it by ML? Right? How do you interpret the coefficients? How do you test the hypothesis? How do you evaluate the performance of the model? Okay. So there are many important research topics for which the dependent variable is limited. What do you mean by limited? It can take values, either binary values 1, 0, or multinomial values 0, 1, 2, 3, 4, but the variable is not continuous. Okay, the difference between a continuous y variable is, of course, it can take as many values as you want over an interval, whereas a limited variable, dependent variable, will take, an example would be a binary limited dependent variable, which will take values of 1, 0. For example, do you work or not work, which could be a 1, 0 variable. Gender could be a 1, 0 variable, right? Okay, so these variables are binary variables. We are going to look at situations where the dependent variable is a binary variable. We know how to deal with the situation where independent variables are binary variables. That is the dummy variable model. Okay, all right. So voting, morbidity, mortality, participant data is not continuous or distributed normally. So we run binary logic or probit regression. It's a type of regression analysis where the dependent variable is a dummy variable, which is coded 0, maybe did not vote, and 1 voted. Now, you see, one way to deal with this, one not a very good way dealing with this, is the ordinary least square regression, where y takes values 1, 0. Okay, we have a gamma plus phi x plus e. Okay, that's the standard one. Now here, the error terms can be shown to be heteroscedastic. And why the heteroscedastic is for you to prove as an exercise, right? But that's not such an important issue. E is not normally distributed because y takes only two values, 1 and 0. So E cannot be normally distributed, conceivably. The more important problem, the most serious problem with this model is that the predicted probabilities can be greater than 1 or less than 0. Right? If this model is probability of y is equal to 1, if the model is probability y is equal to 1, right? Then gamma plus phi x, if gamma is positive, phi is positive, a large value of x will mean a value of the y variable which is greater than 1, which is not possible for a probability. Right? So what we need to do therefore is, okay, right, we'll just take an example here. So what factors determine, we're taking the database base from R, called the Swiss labor force participation. Okay, the question is what factors determine whether a given individual will participate in the labor market. So we have a binary dependent variable 1, 0. Okay. Yeah. So we have, what is this data? It's a data frame containing 872 observations on 7 variables. What are these variables? Whether a person participates in the labor force or not, whether somebody is actually working in the labor market or not working in the labor market. That's coded 1, 0. Okay, that's a factor. Right? R would call this a factor because it's a qualitative variable 1, 0. Income, okay, logarithm of non-labor income. That's the other variable. Now, obviously, if you want to explain labor force participation as the dependent variable, you cannot have an individual's labor income as an independent variable, because the individual's labor income would be determined by whether the individual participates in the labor market or not. So x will be a function of y. There will be a clear case of endogeneity. But whether a person works actually depends upon whether a person is rich or poor. If you are very rich, you won't really work in the labor market, right? So therefore, the determinant, the income determinant should be non-labor income and not labor income. Okay. Age in a person. This is age in decades. So if you're 42 years old, that will be 4.2. Okay. Education, years of formal education. How many years have you been educated? Right. young kids, number of young children under 7 years of age. The idea is that if you have young children under 7 years of age, you are less likely to be working but more likely to be taking care of them. You have older children, old kids over 7 years of age. And finally, a foreign factor. Is an individual a foreigner or not a foreigner? Right, which is a 1-0 variable again. Right, if you are not a foreigner in Switzerland, you probably have no option but to work. Right, so that's what it is. Okay, and the data are, it tells you where the data are from. Okay, it's from Jerfin M. 1996, Parametric and Semi-Parametric Estimation of the Binary Response Model of Labor Market Participation, Journal of Applied Econometrics. Okay, this is where the data are from. So how do you get the data? You run an R program. Okay, inside R you load the library AER. Okay, then data Swiss labor, so that it reads the data Swiss labor in AER. Attach Swiss labor, it attaches the data frame. Okay, and then this, the last line will only print out the data for you. Now if you summarize the data, what did it say? Participation, it says there are 471 people saying no and 401 people saying yes. So out of the 472 people, individuals who are covered by the survey, 471 were not participating in the labor market, 400 were participating in the labor market. The mean income is 7.187. Of course, it's the natural log of income. So, 7.187. The mean age is 20, not 2. Okay, right? Mean age is 20. Education, minimum education is, sorry, the minimum income is 7.187. The first quartile is 10.427. The mean income is 10.686. And so you have the summary of the data. Okay, right? You have the summary of the data. The mean age is 20, the max age is 62, and the mean age is 39.96, so roughly 40 years. Education, minimum education is 1 year, maximum education is 21 years in the data. As you can see, the mean years of education is 9.3. Okay? Young kids, the maximum number of young kids under 7 is 3. Okay, and the minimum number of young kids 7 is 0. Maximum number of children above 7 is 6, okay, in the data. There are 656 people who are not foreigners and 216 who are foreigners. So that's the kind of a data that we have. Okay. Now you see, if you want to see how, if income differs by participation. Okay, income differs by participation. So people who do not participate in the labor market have different levels of non-labor income compared to people who actually participate in the labor market. Right? So if you say you use this command, tapply income participation summary. So what does it say? Take the data on participation, okay, take the data on income, classified by participation. That is, get me separate data for no and separate data for yes and summarize that. So what do you find? You find that the mean income of people who are not participating in the labor market is 10.750. Whereas the mean income of people, these are non-labor incomes, of people who participate in the labor market is 10.610. So there isn't much of a difference. Right? There isn't really much of a difference between the two. If you look at the participation and age, okay, so age is on the x-axis, participation is on the y-axis. The chance that, okay, right. What can you infer from this? Age is a kind of a proxy for experience. Right, so what can you figure out from this?
You have maximum people employed at the age of 30 to 45.
Yeah, so as age increases from 20 to say 3.5, 35 to 40, the chance that you are working in the fraction of people who are working relative to those who are not working actually goes up. The white color represents people who are the fraction that's working. The black is the people who are not working. And then as age crosses 45, then the data shows that as age crosses, people who are above 45 are actually less likely to be working compared to working. Right? Okay, so age does not have a linear relationship. The chance that somebody works first increases with age and then falls with age. The probability that somebody is working first increases with age and then declines with age. You can see it from here.
So what is that? 0 from 0 to 1?
That is the fraction. So, you know, this would be 1 to 0. This is just a proportion of people. So how do you read this? For example, this would mean that 60, this would stand for about 60%. Right? So it tells you how to read these heights. Okay? Now what do you say about education, labor force participation and education? As education increases, labor force participation increases up to 12 years of education and then falls a little bit, right? But the fractional fall isn't very great. You see, as education increases, you are less likely to work up to a point, and then when education crosses 12 years, you are more likely to work. You are more likely to work, right? So the black bars become smaller. The black bars become smaller, but the difference isn't really so dramatic. And actually beyond, at the extreme end, there's a little bit of an increase here.
So how is it possible that less than 6 years and greater than 12 years have the same level of employment?
Well, all it means is that as you are, because you're spending more and more time in school, you're less likely to be because there are also people who are, so these are about 20 years of age, etc. So all that it says is that you're more likely to be working once you cross 12 years of education. Or you are more likely to be working if you're relatively less educated. If you're working because you've not gone to school, or you're working because you've completed schooling, a substantial number of schooling, and in the labor market. And then there's an intervening group here, right, who are educated a little bit, who are not at both the ends, but who are not really likely to be working, related to these two groups. Okay? Yeah, so as you can see for this. So we run a regression model. Yi is equal to alpha plus beta 1 non-labor income I of the ith individual plus beta 2 education of the ith individual plus beta 3 age of the ith individual plus beta 5 age square plus beta 6 the number of young kids plus beta 7 the number of old kids plus beta 8 whether a person is a foreigner or not, and EI. Now actually why do we need a square of the age? This is non-linear relationship. So so what does it mean? It says that delta yi by delta age is equal to beta 3 plus 2 beta 5 age, right? So it means that if beta 5 is negative, and suppose beta 5 is small and beta 3 is positive, then at low levels of age, delta y by delta age will be positive. As age increases, delta y by delta age would end up being negative, right? So you will get a curve like this, right? So that's how you capture a nonlinear relationship. But actually in the rest of the PPT, I have not included h square. I'll tell you why, okay? Fine. So we'll run a simple model, right? So we're estimating the linear probability model. As I said, these are problems with the linear probability model. Okay? The error term is heteroscedastic, estimate probability may exceed 1, the error term is not normally distributed. So what do? You attach the data set, you run a model called the LM, right? Linear model. You create an object called mod, which is linear model, bracket, as dot numeric participation. Why as dot numeric? Because there participation is coded as yes, no. But I need to convert it into 1, 0. So I tell the computer that think of this as a numeric variable, as dot numeric participation, regressed on income, age, education, young kids, old kids plus foreign. These are all the independent variables, right? And where is the data coming from? Swiss labor. And ask you to summarize model. Like I told you, I have not included h square in this for some reason, which I will discuss. Yeah.
Why did you mention that yes is 1 and no is 0 for participation?
That is coded in R.
Okay. Then yes will be taken.
Yeah, yes will be, and it will tell you, if you do the regression, tell you what is the base level that it's, what it is regarding as 1 and what it is regarding as 0. That it will tell you. So if you do a regression, I am sorry for the small font, but this is the output. What is the output? The intercept is 3.624504. The coefficient of income is minus 0.167916. Age is minus 0.105225. Education is 0.00723. Young kids is minus 0.259. Old kids is minus 0.025. And foreign is 0.28. Foreign, yes. So foreign, yes is coded 1. That's what R will tell you. Right? Okay. Now, this is the standard error. What is the standard error of alpha hat? Can you tell me what do you mean by the standard error of a coefficient? You know that beta hat in the regression is a random variable, right? So beta hat has a variance. What is the formula for the variance of beta hat? Sigma hat square upon summation xi square. If you take the square root of that, you get the standard error of beta hat. So these are all the standard errors, right? So what you will get is a x dash sigma square x dash x inverse matrix. The x dash x inverse matrix will be 1, 2, 3, 4, 5, 6, a 7 cross 7 matrix, and all the diagonal elements will give you the variances. So if you take the square roots of that, then this will be the standard errors. The t value here is testing for the null hypothesis. For example, here it's testing for the null that alpha is equal to 0. Right? So what will be the t statistic here? Alpha hat minus alpha upon the under root of upon the standard error of alpha hat, right? This will be a t distribution with n minus k degrees of freedom. The null hypothesis alpha is equal to 0. So this will be alpha hat upon the standard error of alpha hat, right? Alpha hat upon the standard error of alpha hat. So this is alpha hat. If you divide with this, the t value is 8.504, right? Now this is an important number. This is called the p value. What is this value? Now what is the t value that you got here? 8.504. Now think of this as the t distribution. The null hypothesis alpha hat is the mean of alpha hat is alpha. So the mean of the t will be 0, right? What is the value for t that we've got? 8.504. So this will be somewhere 8.504.